Pretty bad at that. So recording again. So in some ways, this is going to be a similar arc. So 4.2 was line integrals. 4.3 and 4.4 are other ways of doing line integrals. 4.5 will be flux through a surface. 4.6 and 4.7 will be other ways of doing flux through a surface. So alternate ways of doing the same thing for special cases. So remember, what you should be thinking of here for a flux is, think of, we have a river, it's flowing downstream, and we have an imaginary dam, and we want to know how much water is going through that dam for a given time interval. So first thing is, so first a little definition. Which will need the background. Which pretty much always is true, but we'll sort of need the background. Also say everything again because it's messing me up. Each point on a surface M has 2 unit normal vectors. The normal vector and the one in the opposite direction, whichever way you want to do it. A surface is orientable a surface is orientable if it will pick one of those orientations on the surface continuously as we move along the surface. And in some ways, it's easy to give an example to show what that means in the opposite. And it kind of tells you what we mean by orientable. So first, have people heard of what's called a Möbius strip? Mobius strip? However you want to say it. Has anyone heard of a Mobius strip? No? Yes? Okay. So here it is. It's actually really easy to make. So Mobius strip is take a strip of paper, and what we're going to do is having a pop-up thing come up for some reason. Is in the middle do one twist. So this is just a regular white piece of paper. In some ways, the fact that the faces are distinguishable doesn't really matter. So we just have this one strip of paper. We twist it so the one on one end is the complete opposite to the other one. So one full twist, and then paste the two ends. And what will happen is, suppose you start on the outside of the Mobius strip. If you then follow a path all the way around once, at the end of it, you're going to end up on the inside. Right. So this is not orientable, because if we try and make it so it's always on, so if we start on the outside and go all the way around, we end up on the inside, which means we need both the normal pointing outward and the normal pointing inward. And obviously we can't jump. So this is something that isn't orientable. And that's what we're talking when it means orientable. For most things, this is going to be fine. So if I take a sphere, if I start on the outside and move along the sphere and come back to where I started, I'm still on the outside. So for most things, this is not a problem, but this is a fairly easy example of showing that it is possible that it's not orientable. Okay. So that's the background. So we want it to be orientable, so we want it to be nice in this sense. And now let's go through the steps to get, let's see, where are we? Ooh, very quickly. We want to get flow through M. This is kind of in the background to get the theory. We'll do the actual example tomorrow. So we want the flow through M goes so in terms of the vector field, the only part that we care about is the part of it that's going actually through. So we only care about the part that's orthogonal. So we do the usual physics thing, which is take the vector field, break it up into parts that are orthogonal and parts that are parallel. And we don't care about the parallel part because it's not actually going through the surface. And therefore, we're going to do this. We're going to take the vector field, I'm not sure why I'm using V instead of F, orthogonal to M. So only part of P orthogonal to M. And that's not an absolute value, just the usual changing my parentheses, is this, which is this is the projection of the vector field onto N. And the reason we don't have a denominator, and this is an absolute value, is since it is a N is a direction, its length is 1. Okay. So that is the part that is orthogonal to the surface, which means that's the only part we care about. And so what we're going to want is, here is the flux. It says surface area. Because what we're going to get is the part of the flow that's going through the field, and then we're going to want to multiply by the surface area of that little piece. So we do our usual integral thing, break my surface into lots of little pieces, and on a little piece, we're going to assume that it is flat. So we can just multiply the area times the rate going through. And so we're going to do a polarization. So a couple notes. Given a parameterization, we know that RU and RV will be parallel to the field. So therefore, the cross product will be perpendicular. And then to make it have length 1, this is really messing me up here. I should have just left off the parentheses altogether. That was going to be parentheses in the top, and in the denominator, this actual length. So ignore these things. There aren't really anything there. Okay, so that's the normal. And therefore, we're going to get something similar to this. So R here is R of B is equal to the parameterization of my service. And D is the values of U and V that will give me the service. And again, what we're doing is, so we're taking the flow perpendicular to the surface, which is this part here. And since n is given by this, when we multiply by the surface area, well, we know from 3.11 that the surface area is this denominator. When I multiply, it's going to cancel. And I'm just going to get the vector field where we plug in the parameterization, and then the dot product, the normal, which is the cross product of the two partial derivatives. So it's slightly more elaborate than what we did with the line integrals, which is the first part is get a parameterization. So the first example, I'll give you a parameterization. Get the normal by taking the two partials and taking the cross product, and then to multiply that or take the dot product of that with V when we plug the parameterization in. So we don't have time today. So tomorrow we'll start off with an example of how this works. And if you're given the parameterization, it'll turn out to be not too terrible. But that's what we'll start with tomorrow. And so for tonight, look at the homework for 4.4. I did one already, but look at the other ones. So as usual, if I will stop now, and you will stick around if you have any quick questions.